everyone. My name is Iannelli. I work for a company based here in New York called Yext, and we largely build brand management software. Two of our biggest products are Knowledge Graph, which is a CMS that users can go and use to input and curate their data sets, and Search, which allows them to configure a search engine to search over this data set. So naturally, I'll be spending today talking about some ways in which we implement search over this knowledge graph. So I'll talk about the problem and what's unique and challenging about search over a knowledge graph over how it compares to regular document search. And then I'll go into the solutions and what we do and what we can do to index and search these knowledge graph entities. And what they largely fall into is we've developed a collection of methods between mapping between natural language space and knowledge graph space, and back and forth between these two spaces. So this is a pretty typical query that we see in our search engine to a customer that's probably like a hospital or something. In this query, we're looking for a cardiologist in Ann Arbor who speaks Spanish and accepts Aetna and is open 24/7. And this is pretty realistic. Probably not the open 24/7 part. I don't know any doctors that are open 24/7. And what you see in this query is that even though it's in natural language, it does have structure. It has entities, it has relations between these entities, and these are implicit to it. We have a cardiologist. This is a physician located in Ann Arbor. This cardiologist can speak Spanish, accepts Aetna, and is open 24/7. And further complicating this is actually what the data looks like in the knowledge graph. Here, let's call her Dr. Ann Smith. She works for a hospital that's located in Ann Arbor, accepts Aetna. Sometimes she accepts different insurance based on the hospital that she's working on, but we won't complicate this example with that. Speaks Spanish and has cardiology as a medical specialty. And what you see here is there's a lot of entities here that we call auxiliary entities. They're not meant to be surfaced in the search. We only ever really want to surface the doctors in this query. We don't want to surface the insurance companies, the locations, the specialties. But the challenge is that all these things that are important to the query aren't actually located on the entity itself. So we still want to be able to index all of these, and get this information into that entity when we conduct search. So we could write the Sparkle query, right? The problem here is that this is meant for lay people. It's meant for the end users of the search engine, searching on the hospital website. And the people that configure the system, so like our users in the hospital, also aren't really ontologists. They do not know how to write Sparkle. So we need like a user-friendly interface to both building the knowledge graph, curating it, and searching over it. So to recap, we want to be able to collect this data from humans, right, in a human-friendly way. That means their customers' existing corpus of documents, websites, PDFs. We want to model this knowledge graph, keeping in mind that we have these auxiliary entities. And we want to be able to output this data, both natural language search and even content generation. So the two techniques we've developed here we call them prose to graph and graph to prose, and this is what I was alluding to before. It's a set of methods that map from natural language space to the knowledge graph, and the knowledge graph back to a natural language space for output to users. So we'll start with prose to graph. This is the high-level architecture of it. Given some input documents, we go through these 4 stages. Entity extraction, so NER, find the entities within some natural language, perform co-reference resolution. Don't worry if I'm going fast, I'll go through an example soon. Entity linking to the existing knowledge base. So we want to be able to take these entities that we've extracted and find where they exist in the knowledge base because they're instances of those entities. And finally, relation extraction. So taking those entities that exist within this input passage and building relations between the two. So we'll start with this example. This is taken straight from the Wikipedia article on 401k. I believe it's the first couple of sentences. In the United States, a 401k plan is an employer-sponsored defined contribution pension account defined in subsection 401k of the IRC. Employee funding comes directly from their paycheck and may be matched by the employer. So step one, find the entities. You can use NER for this. It's a it's a pretty well-established problem, so I'm not going to go delve too deeply into this. There's lots of libraries that will do it. It's a pretty simple structured classification problem. Co-reference resolution, so find the entities that refer, or the instances of the entity that refer to the same entity. In this case, employee in there. And then we link them to, in this case, I'm using Wikipedia as an example, but we want to link it to whatever knowledge base the customer has. And finally, the relation extraction. So here we have 401k is an instance of a pension. 401k is defined by the Internal Revenue Code. So yeah, again, not going to go into NER, but the two problems that are pretty interesting here are entity linking and relation extraction. And we're using some pretty modern techniques for these. The first one we'll describe is entity linking. So we have this little snippet of the section here. We generally use a greater context, but for the purpose of this example, this is what we've got. And the entity here is placed in something called a mention vector, and then we take its context window. So here, the United States, a plan is an employer is its context, and 401k as a mention vector. We compose them, and this composite vector, you can use concatenation. I believe the original paper that this is based on, it's actually based on Blink out of Facebook a few years ago, uses concatenation, but you don't necessarily need to use that. We don't use that. And then you search a vector database where you've also indexed your knowledge base. So here we've got 401k, and you see like this matches to the 401k article. Relation extraction is a little bit more interesting. This is based out of some work out of a year's group presented at SIG-IR and NAACL last year. And to do this, it's kind of like a confluence of several different language models. So we've got all our entities that we've extracted using NER. And we take a sliding context window and emit every pair of entities within that context window. And these are candidate relations that we're going to score using an entailment model that will make up the edges for our potential knowledge graph. So it's important that we use the context window here, because if we don't, the number of candidate relations just kind of explodes. So this keeps the algorithm scaling roughly linear instead of quadratically. So in this example here, we have three candidate relations: United States 401k plan, United States pension account, 401k and pension account. And then we have a bunch of human-created templates for specific relations, in this case, instance of. So a human has gone and actually created these natural language templates for what an edge, what the instance of edge will look like in natural language. So here, noun one is a noun two, noun one is an example of noun two, noun one is a kind of noun two. And then what we do is we fill these out with our candidate relations. So here, because we've got three different relations and three different candidates, you see that we have nine different filled-in templates. So you can see how this sort of gets expensive, right? Like there's many different statements that we have to score here. Right, so now we take all these statements and we take the original passage and we input them into something called an entailment model. So an entailment model is also an NLP type of model, and what it does is it takes two statements, two passages, One is the premise, and the second is the hypothesis. And it scores whether or not you can conclude the hypothesis from the premise. So here we're using the original passage as the premise, and each of the completed templates as the hypothesis. And the entailment model tells us whether it is true, whether the premise entails the hypothesis, that's true, whether it contradicts it, that's negative, or neutral, whether you can't conclude one way or another. So in this case, the example that we have here, the United States is a pension account. The United States is an example of a pension account. The United States is a kind of a pension account. We actually get neutral out of all of these. So this is a textual entailment model. So even though this sounds ridiculous that we're not getting negative, you actually can't conclude that from the passage. For this other example, 401k plan is a pension account. 401k plan is an example of a pension account. So you see also how there's some duplicate work here, and you don't always get positive out of them. But positive means that this edge does exist in the knowledge graph. And it's not always perfect. It's up to you how you want to manage the precision recall trade-off. We use majority voting, but yeah, basically that. So the second thing I want to talk about is graph to prose. How do we go from the knowledge graph space to the natural language space? So let's talk about how search works in order to actually get to these ideas. You've got a corpus of documents, and you want to find a document that matches a query. So you're going to take these documents, and we're going to talk about dense retrieval here, right? So like dense vector databases. You're going to use some embedding model to project them into vectors and index them using some vector database with either like HSW in the backend or LSH, some type of vector indexing scheme. And then when a query comes along, you're going to project it to the same vector space and conduct nearest neighbor search on those documents and hopefully find the entity that you're looking for. In this case, cardiologist, you want to get the cardiologist out. So there's various different ways of improving search. And one of those ways is query expansion, and it also has a complement to document expansion. That's taking the query and taking the document and stuffing a bunch of keywords, questions, adding more words to this document and query so that the indexer actually picks it up and they show up as results when you're searching for it. So the technique displayed here comes out of a paper that introduced a model called doc2query. And again, this is dense retrieval. So what it does is take in an input document, run it through the model, and out comes a bunch of queries that a user might use when searching for this document, answered by the document. So in the process itself, you're taking all these predicted queries, concatenating them with the document, and then just these become your new documents that get indexed by the search engine. So what we do is we take this model and we want to apply it to entities. So like in entities, you can't really, again, remember, there's nothing really there to index. There's no real text. Dr. Anna Smith, everything that's important about her that's related to the query is in her neighborhood. It exists on other entities connected to her. So we want to be able to take this technique and apply it to our entity space. So this is what our entities look like in the knowledge graph, a bunch of JSON objects and some relations between them. And we use this technique called EntityExpansion, where we take this, this is roughly the kind of prompt we use to the language model. Given the following JSON representations of entities in a knowledge graph, describe in plain English the entity, and then also generate a list of potential queries and keywords that a user might use when searching for this entity. So then you take this, input it into your language model with that engineered prompt, and out comes a description of the entity, right? And this is indexable and can be searched using a regular search engine, and a bunch of candidate keywords and questions that a user might use when actually searching for this entity. So what we found is This is actually pretty useful. One, because like we have no other real way to do vector search over entities. But we've also found that it's useful not just for natural language search, but for generative AI use cases. Slightly related to Diego's talk right before mine, when using it for chatbots, when using it for generative AI, this strongly reduces the chance that your model is going to hallucinate. The paper we have here, also called Knowledge Injection, is going to be presented at ESWC later this month, 2 weeks from now. And we've shown that we actually do get like some pretty impressive results in reducing the number of hallucinations in it, and also increasing the number of facts included in the output. In many cases, the language model, when not given this information from the knowledge graph, will essentially just make up its own facts, right? Make up fictitious phone numbers, fictitious addresses, and so on. Yeah, so rushed a little bit, but that's pretty much all I have. So I'm happy to take any questions. Yes.
Do the queries perform differently based on the domain of documents? Like, is this sector specific or is this like sector agnostic?
No. So this, I used healthcare here as an example because it's a good use case where like the doctor entity has no information on it when you're searching for a type of doctor. But no, like this is not domain specific. This technique works on anything as long as you have the underlying knowledge graph. Yes.
Can you talk more about your entailment model? Is that like your guys' invention, or is that pretty common?
No, it's pretty common. Yeah, so like you can download one off Hugging Face right now. You probably have to go to like a paper to get the documentation, but usually like it outputs 3 classes. One is, let me go to it. Given statement 1, statement 2, 1 is typically positive, outputs 2 if it's negative, meaning contradiction, and 3 meaning neutral, which you can't predict one way or another. Yes.
In the results you showed in the last slide that you're going to present next month. So I think the sample size was like 60 or 70. So can you comment on like how that relates to maybe the size of the graph that you used for generating the expanded, text?
Yeah, so the graph itself, so we were piloting this with, this is actually real data, so I'll be very careful in what I say here. We were piloting this with real customers. So there were not a lot of examples in that test set, and not a lot of examples that could be labeled. So that's primarily why we were doing with this. So we were using it in the case of location reviews, right? So think like restaurant reviews and responding to those reviews, and hotel reviews. So for size of the knowledge graph, think like the locations where these restaurants or hotels are. Yes.
Do you have an ontology for this graph, or why do you have to extract the relations and not just the verbs or something like that?
Right. So there usually is no ontology. This is the target customer is the layperson. So there usually is no ontologist at the other end using the product. We really look at just taking entities and relations, and that's kind of how we define the knowledge graph here. Okay. Yes.
So the little description you generated out of the graph.
Mm-hmm.
Do you have a useful size for those? Like how big or how small have you done?
That's a good question. And luckily, the customer knowledge graphs that we use tend to be relatively sparse in comparison to something like DBWiki, right, or Wikipedia, you'll find that like trying to put in every edge from something like DBWiki will even fill up like GPT-4, right? And it can get very expensive very quickly. So we haven't run into any issues of size yet, but it is something that we do look at, trying to compress the queries and like trying to come up with a good neighborhood sampling technique to find the most important entities. Unfortunately, nothing super concrete yet. That we find. Okay. Hi. I'm not the one presenting. My colleagues will be there. Yeah, same. Sorry.
Sorry, I missed this one.
Let's see my card. Yes. For my brother.
Do you mind back?
It's okay.